Hello. Okay. Hi, everyone. Thank you for coming, and thank you, Ingonyama, for inviting us. So, I'm RJ, or Roberto, and he's Diego.
I am Diego. Thank you.
And we are from EigenLayer and Lambda class. So, this is a new protocol we're building that was born inside of Lambda class, and is being developed by a new company with help of Lambda class. So, I will start creating a little background on what the company Lambda class is doing, so it's easy to understand why are we building this and the perspective of how we're seeing the problem in itself. Because the history of the people building this makes a lot of sense in the end of why are we actually trying to solve this problem for ZK and why do we believe it's useful for many use cases. So Lambda class is an engineering company and it has been working in the ZK space for a while across the whole space with many different proof systems. And one of the things we notice is there are a lot of great tech. ZK is accelerating and moving really fast. We have now a lot of new proving systems. And we believe that some of these teams will solve and are already solving many of the problems we have today. But in the end, many of these teams, we believe, are going to have a problem on integrating this in Ethereum. So what we're saying is, okay, proving is getting better, but what we need to fix in the future is verification. So yes, today we're speaking of what is aligned, what exactly are we doing, a little bit of the history of blockchains in itself, so you can understand the perspective of why Align is important for the future of scalability and many other use cases, and some use cases, and then Diego is going to talk about the architecture and the prover and the testing we have going on at the moment. So, what is Aligned? Aligned is a universal verification layer. In specific, it's a universal ZK verification layer, meaning the only thing we do in this decentralized network is verification of ZK proofs. Why are we doing this? Because we want to offer cost-effective and fast verification from proof. The idea is to not only offer this for a lot of proof systems, but benefit Ethereum in the end. So the idea is to build an infrastructure that can help Ethereum be a better verifier. And we have two modes. One is a fast verification, and the other one is an aggregation mode. And we can discuss that later on. So why do we need a line layer? In specific, we need it because Ethereum is expensive. It's quite expensive for many proof systems to verify on Ethereum. Maybe others are actually subsidized and are quite cheap, but that means there's a not fair market for verification. That means some proof systems are quite cheap compared to others that are expensive. And we think that in the future we'll see many proof systems, and the infrastructure for ZK should be quite open to that. So we want to create a new market where everyone is a third-class citizen in the ZK space. And the other thing is we want to simplify bridging, and we want to reduce latency. Because most teams, what they do is they do aggregation in the end to amortize cost, and that comes with a trade-off in latency. And for some use cases, this could be quite a problem. So let's recap a little bit with the blockchain history. So all of this started with Bitcoin, right? It solved the trust problem. It allowed people to do peer-to-peer payments without needing to trust or minimizing the trust on third parties. This is great. It's still working. It's one of the best innovations ever. But the problem is, if you wanted a new use case, you need to bootstrap a new network from scratch. So then we got Ethereum, right, that solved this problem by allowing anyone to create an application on this decentralized network, but consuming a certain amount of block space that is limited. So the problem we have is scalability, because everyone needs to re-execute the same computation, and we want to maximize decentralization in the end. We solve that by using L2s, because we can use, for example, zero-knowledge proofs to use the block space in a more efficient way. The problem we had is fragmentation of liquidity and users as well. So recently, we got EigenLayer that allows us to use the trust network or the infrastructure of Ethereum to build new protocols. This is super useful, especially when you want to create new features for Ethereum in particular. I think Brevis, for example, spoke about a ZK coprocessor a couple of minutes ago. What we are going to explain today is how we use EigenLayer to create or enhance a new feature for Ethereum, in particular, verification. So EigenLayer offers fast and cost-effective verification by creating a new protocol using EigenLayer for security. So we're going to use risk-taking that allows us to create a new protocol using the validators of Ethereum with one particular purpose. And that particular purpose is only verification. And this is important because we are only focusing on one problem and trying to improve this for Ethereum and other protocols as well. Okay, and this is not maybe something common for this conference because we're going to speak about a protocol that has nothing to do with ZK, that is EigenLayer. So what they are doing is introducing a concept of risk-taking. This means that you can use your stake ETH to participate in protocols that are not Ethereum in itself. Meaning that if you have a validator, you stake ETH, you can now use that collateral to validate and participate in the consensus of a different protocol. This is what people will do when they want to run a EigenLayer in specific. So they will use their stake ETH in order to participate in the consensus and the security of this new network. This is especially useful because you can amortize capital costs because anyone that risk-takes can participate in many new different protocols. And at the same time, it helps you create new protocols without having to worry about the block space of Ethereum. Because now you have a new complete dimension to actually create and innovate on Ethereum. So what we're doing is using this to create and enhance the feature of verification for Ethereum. So with this, we can open the ZK space, the ZK design space for Ethereum, because we can easily bootstrap a new network that is connected to Ethereum from the infrastructure side and offers really strong cryptoeconomic guarantees. And we don't have to create a brand new L1. We can just use Ethereum as the main asset. That is super important because it's quite hard to create a decentralized network with a brand new asset that actually can back and be the secure asset the proof of stake needs. So some of the use cases we see and we believe are going to be really important for what we're building is fast finality for rollups and app chains because we have very low latency. So without needing to, in many cases, while you're doing aggregation, you can just send us the proof and you can get a really fast verification that can be extremely important for interoperability protocols. The other one is fast bridging. Maybe you are just an app chain that wants to use aligned by itself and you will get a really fast instant settlement. The other one is that you can use aligned as a modular component and start building new protocols that weren't possible before. For example, if you use aligned plus a new data availability layer, you can offer a really fast and cheap settlement layer. Now, the possibilities are huge because what we're doing is opening or lowering the barrier of entry to many ZK applications. And this is possible because we are creating a brand new infrastructure from scratch, only thought with the only citizen being ZK proofs. And some of the other use cases that we haven't seen on-chain yet, but with this will be possible, are ZK oracles, on-chain gaming, and verifiable machine learning as well. So we believe this is going to open a lot of new use cases.
Well, then let's jump a little bit on the architecture of EigenLayer. So this is the basic idea. EigenLayer will receive lots of proofs of different types from like different clients, for example, Plonk proofs, Stark proofs, Graph16, BNews, whatever you like. These proofs will be stored in a data availability layer, and the operators of the of EigenLayer are going to run the verification algorithm for each of these proofs, and if we reach consensus, these results will be posted in Ethereum in a smart contract, and then anyone can go and check whether those proofs are valid. Now, since we want also Ethereum to be able to verify all these proofs, what we offer is a proof aggregator. This is going to take all the proofs that we verified so far and generate a single proof via proof recursion that attests to the validity of all those proofs. Okay, so this is like the basic structure. This is the base design. So there is a task manager that posts the different tasks to Ethereum via, for example, some metadata and the proofs hash. It also posts the proofs into the data availability layer. The operators are going to fetch the task, fetch the proof from the data availability, run the verification code, So here there is like no Solidity code. You can run directly, for example, Rust code. So it's more efficient. And each of the operators is going to send to the aggregator the result of the verification. If the aggregator sees that there is consensus, then it's going to aggregate the results and post them in Ethereum, okay? And then, of course, what we do with all the several proofs is first we can use, for example, some general type prover, such as Jolt or risk 0 or SP1 or whatever, and perform the recursive verification that makes all the proofs be in the same format. So we get, for example, a risk 0 start proof, and then we can do recursive verification using that tree and get the final proof. If we need to further compress to reduce cost in Ethereum, then we can do a final wrapper to something like Growth 16 or Plonk. But there are like plenty of opportunities and tools to use here to bundle all the proofs together, okay? And so we are almost ready to have the testnet with EigenLayer, but we couldn't wait, and so we deployed this using Tendermint. And there are like several provers that we support that you can play with in this testnet. We have Kairos Plonk, Kimchi, SP1. Funny, we added Jolt just yesterday, so it's outdated. And while we are working on adding Risk 0, Pickles by Mina, Growth 16, so we can easily add any new proof system that we have, its verifier, and have its proof verified here in EigenLayer. And well, this testnet was the first decentralized verifier network. It was launched like 2 or 3 weeks ago. It had over 300 validators, lots of people who wanted to participate, and they could do it with just 2 proof systems, but we've been adding like more stuff and testing it quite a lot to see what's going on, how people think about this technology. And well, I think that if you want to see what we are doing, you can join us in X, Telegram. We have a Discord server to discuss things related to the testnet, and of course, all the GitHub repos, which are always open source. So thanks a lot. And if you have any questions, we'll be more than happy to answer.
Any questions from the audience? Oh, here.
Yes, excellent talk. I was wondering, how can you compare the gas saving cost of running verifying proofs on a line layer with actually verifying them on a layer 2 or on a cheaper gas blockchain? How does that compare?
So we are aiming, I believe it's 90% cheaper for now. We're doing more benchmarks because it depends on the proof system as well. Intuitively, what you need to think is, okay, this computation is going to be done in a new network that is just designed to run verifiers that take around 100 milliseconds, I believe, in a normal computer. And the main cost we will have when we need to use a like layer is going to be the data that is posted in Ethereum, that is just the hash of the commitment of the proof with the public inputs, and the result that is true or false. And then also the verification of the BLS signature, that is one of the problems that many of the ABSs in the EigenLayer space have, but that's been fixed by EigenLayer, and we also have some solutions of how to wrap that in a snark and to actually scale with the amount of operators we have. But we will post like better benchmarks soon. Right now we have a draft of the white paper that describes the architecture. The testnet is working, but we need to do some more specific benchmarking so you can have like, okay, if I use a Stark, this will be the amount of gas actually used or not. But it will be around 90% from what we have been testing.
Excellent.
Thank you.
It's just a comment. I really love what you guys are doing. Great.
Thank you.
Thank you.
Maybe I'm misunderstanding a little bit of the architecture, but at the final stage, when you have the final proof, which is the aggregation of this tree of all these proofs. How much data are we going to have to provide along with that proof to be able to utilize it for like a very specific application? Like, how big is this tree? Do you imagine?
No, to verify the proof, you only need information regarding the public input and the proof you're using. Of course, when you recurse, you can compress the public input by providing a commitment to a public input. That is a standard technique that you used in recursion. Because imagine that if you have this binary tree, but you never compress the public input always grows linearly with the number of proofs you are aggregating. So there are like some ways of reducing that, and you only care that your proof has been verified in aligned. And also, you know that if the final proof has been verified and your proof has been aggregated into that gigantic, or it's not gigantic, but the final proof, then you know that it was valid. You have these two modes. In some cases, you want this fast verification and very cheap. And if you want like to be extra sure or whatever, you can wait for the final verification in Ethereum, but you get to batch lots and lots of transactions. This can be also like a big roll-up, taking lots of transactions. It can really help ZK scale by providing like very cheap verification.
Thank you.
Thank you.
Thank you guys for the. It's here.
Oh,
the
we
right,
got a lot
on
of
the right.
questions.
On the right.
Oh my God.
Quick one. You mentioned both EigenLayer and Tendermint, and I'm struggling to understand how these two mix up. Do you intend to sunset Tendermint when EigenLayer actually has ZK proofs, or do you not intend to launch on production until EigenLayer actually has slashing conditions? Like, what's your strategy there of having both?
Yeah, so the Tendermint version was a proof of concept because we wanted to go into testnet pretty quickly and to test the actual limits and, okay, what will happen if we actually have a decentralized network like this? Because you could go into testnet with Eigen, but we wanted to do the full end-to-end testing. So right now, we are migrating to the EigenLayer testnet, and the thing that will be in production in 5 months is going to be the EigenLayer version. The Tendermint one, we're using it for a proof of concept, and it was only that. We did that, I think we developed it in like 3 weeks, with the only purpose of proof of concept testing and seeing what are the limits, for example, for the transactions, the size of the transactions, and which proving systems we can include easily or not.
A follow-up question. What would constitute the slashing conditions in aligned layer?
Yeah, so we have a short-term plan and a long-term plan. The short-term plan, it will be, okay, once we go into production, the slashing mechanism will be subject to slashing. Meaning if you're the minority, you say, okay, this proof is incorrect, but all of the other operators are true, you will get slashed, okay? That is not perfect, because you are also not leveraging some of the features that EigenLayer provides, so you can have, for example, objective slashing. So you could run directly the computation of the verification on-chain and then say, okay, the outcome that EigenLayer achieved is actually wrong, so the operators that decided that this outcome is true, we can slash them directly. What is some of the trade-off we have to take there into account is that each verification will be different, the cost of running the computation on-chain. So for that, it will take us a little longer to actually test things and have into account like the costs and how much economic at stake is per proof as well. So we can create a really good and robust slashing mechanism. But once we go into production, it will be a simple subjective slashing. We believe it should be a really decentralized network because the software we're running in the operators is super lightweight. So we could have a lot of operators running this, and we are solving the problem of adding a lot of operators regarding the aggregation of BLS signatures.
I think I missed the fee mechanism. And I was wondering if you're still incentivized to use, for example, if I have a Stark proof, it costs more to verify than a Gross16 proof. Am I still incentivized to use the cheaper verification mechanisms?
No.
Okay, I see.
No, that's the way we live. This is so important. Okay. Here, all the proofs are going to be first-class citizens, like verifying a Stark proof directly in the computer it's super cheap. So in this case, what we're aiming is, okay, for now the fees will be, we will take how much it charges a Stark proofs and say, okay, we'll charge 90%, kind of similar to a fee mechanism some L2s have. Because we need to, the user needs to pay in advance for the fee we will pay directly on chain. The good thing is our system is also highly scalable, so we shouldn't have a long-term problem with fees.
Okay, thank you.
Yeah, it's a very good question. I'm just curious, how aligned are you?
Pretty much aligned.
Very aligned?
Yeah, definitely aligned.
Nice.